Peace be upon you all. My name is Fatima Gerber Yusuf and this is Electronics. So today we are going to talk about an aspect of material science, which is engineering and true stress and strain. So as you can see from this graph, this is actually depicting the behavior of true stress and strain of a material, as well as its engineering stress and strain. Usually in calculations, what we use is engineering stress and engineering strain, but that's actually an approximated value, because basically when a material is put in tension or it's pushed in compression, its length changes, its area changes. Basically, for example, if you have a rod like this, if you were to pull it, that's in tension, of course its area will change and also its length will change. The area will reduce. This is so that the volume will remain constant. So you'll be left with something like this yellow rod. But when it's pushed in compression, then the reverse will be the case. Hence, instead of having something like this, when you push it, obviously the length will reduce to be something like this, but the area will increase. That's the diameter will increase to give you something like this. As I mentioned earlier, this is to maintain the constant volume such that V1 will be equal to V2. And for V1 to be equal to V2, your original area multiplied by your original length should be the same as your final area multiplied by your final length. So usually in calculations, we only use the original area and the original length, which will give us an approximate value of engineering stress and engineering strain. But in the true sense of things, this is actually just easier. But in the true sense, we are supposed to have values that are depicted in this true stress and true strain graph, and this is gotten by using the values of the final length of the final area and stuff like that. So then the formula that is used for engineering stress and engineering strain is such that engineering stress is depicted by this symbol sigma, and it is given by the force or the load divided by the original area. As for the true stress, it's depicted by this sign with a small t below it. And here, when you have your force, which is unchanging, the area you are going to use is going to be the final area. As for strain, it's depicted by this, and it's supposed to give you extension divided by your original length. While for your true strain, it's going to be an integral of your change in length. So when you integrate this is actually going to give you L, right? This is 1 over L dl. 1 over L differentiated with respect to L. So this will give you the ln of L. So when you open this, it's going to give you ln L F minus ln L0. And when you combine them under a single ln, it will give you ln of LF over LO. So that's your true strain. But then you can further simplify your true stress and your true strain. So let me change the color of my marker. As for true stress, since your formula is F over AF, right? So you can go back to your formula for constant volume. That's your V1 equal to V2, given your original area multiplied by your original length. It's supposed to give you your final area multiplied by your final length, but sometimes you're not given your final area or your final length or something like that. So the way to do this is you can express your through stress in terms of your engineering stress. And how do you do that? By switching this up. You can express AF to be equal to A0 LO divided by LF. Alright, so when you are going to divide, or when you are going to calculate your through stress, it will give you F divided by all this, right? Divided by AO LO over LF. Now this LF will come up here, so you'll have F. So you have F LF divided by AO LO. But you can recall that F over AO is actually the same as your engineering stress. So you can factor it out to give you your engineering stress multiplied by LF over LO. So you can either leave it as at this, or you further simplify your LF over LO. And how do you do that? By using your formula for your engineering strain. That is, we know that engineering strain is equal to LF minus LO. In tension, your final length must be greater than your original length, and all this divided by your original length. So you can split this into LF over LO minus LO over LO, and this will automatically cancel to become. So what happens now? You can express your LF over LO, which is this, in terms of your strain and 1. So you have LF over LO. Your LF over LO will give you your strain plus. So your through stress can be represented by your engineering stress multiplied by your engineering strain plus 1. That's it. As for your true strain, you can remember that when we brought it out as the integral 1 over L dl from original L to final L, what we got was ln LF over LO. We can simply adopt the simplification of our LF over LO, which is engineering strain plus 1, such that our through strain could be equal to ln, such that our true strain will be equal to ln of engineering strain plus 1. So there you have it. Your through stress is equal to your engineering stress multiplied by your engineering strain plus 1 in bracket, while your through strain is equal to the ln of your engineering strain plus 1. So with this, you can relate your engineering strain and your through strain. You can also relate your engineering stress and your through stress. So thank you very much for watching. We can meet in subsequent videos for examples, solved examples on this issue. Goodbye.